Okay, let's continue with our calculus of variations. A very useful discussion for uh, a very useful discussion of whatever we are going to cover today can be found in this classic book by Courant and Hilbert, Methods of Mathematical Physics, Volume 1. Let me write it down here. Courant and Hilbert. Okay, Methods of Mathematical Physics, Volume 1. Methods. Physics, Volume 1. It's a very nice classic book, and I would encourage you to have a look at it. Okay, so I gave you a few examples where we need calculus of variations. For example, I was asking about what's the if I want to know that curve which minimizes the distance between these 2 points, okay, the length is minimum between these 2 points, what is that curve? Okay, that's one question you can ask. And also you can ask about the what should be the shape of this curve so that you get the minimum area of revolution around the x-axis. Okay, so you again need to minimize an integral of this kind. Okay, so in general we are going to be looking for minimizing or extremizing integrals which are of the following form. So you'll have some functional j, okay, it doesn't look like j of y, where y is a function, and the two examples I showed you have integrals of this form. So they are all integrals over one variable x, and then you have a function f which depends on the curves y and y prime. Okay, the functions y and y prime. Okay. Now you may immediately realize that this question of looking at the minimum or minimizing these integrals can be asked in more general situations. For example, you could, let me write it, generalizations. So you could have a situation where instead of having just one function y, okay, this y prime is the derivative of y with respect to x. So a generalization would involve, for example, instead of having just one function y, you have several functions, y1, y2, and so forth to yn. So let's say n of them. So j is a functional of all these functions, and you have again the endpoints I have fixed here, and then you have dx f, okay, and then you have x, y1, so forth to yn, and then you'll have all the derivatives of y1 and all the remaining yn prime. So that's one generalization possible, where instead of just one function y, you have several of them. You can still think of more cases, more generalizations, where you may have not only one variable x here, but a multiple of them. So let's say you have two x1 and x2, and let me denote that generalization by putting only one variable, one function y here. So you could have like x0 to x1 sorry, not x0 to x1. Now you will be integrating over some region R in the space spanned by x1 and x2. Okay, and then you have your function f. As I said, there are two now, x1 and x2, and I'm still keeping one variable, which you can have. You can of course have more than one, and then the derivatives of these with respect to the two variables, dx1 and dx2. Okay, that's one generalization possible, and you can have still more. So instead of having only the first order derivatives and the function here, you may have higher order derivatives also present. So let's say that I have let's say from x0 to x, I'm looking at only one variable right now. So you have some function f, which not only depends on the function y, but also its first derivative, second derivative, and so forth, let's say up to nth derivative. Okay, so you may ask, like, I want to minimize such an integral. Okay, so there are many generalizations that are possible. Let's begin with our first one, the simplest one, and try to see what y, the curve y, will give the extremum for j. Okay, that's the question we want to ask. Let's see how to proceed. So let me write it down again. We are looking at extremizing our j of j is the functional, and first thing is my limits of integration are fixed, dx f x y y prime. Okay, also the values of the function y at the endpoints are specified. So I'm going to search for all those functions y of x. Okay, search among all those functions whose endpoints, the values at the endpoints are fixed. So I'm saying when I'm searching for the function which is going to extremize this integral, I should keep the values of yx at x0 and y at x1 to be fixed. Okay, these values cannot change. Okay, so let's say here is x0 and there is x1, and I'm looking at some y of x. So the value here and the value there is not allowed to change. So that's the thing. Yeah. Now let's see. Our goal is to find out the y which will extremize this. Okay, which is equivalent to, I mean, in the parallel for functions, if it was a function, not a functional as here, you know the answer. You just have to look at the first derivative to be vanishing. So all those points where the first derivative vanishes is going to provide you the answer, and we want to find the equivalent thing here for the functionals. So let's say this is the solution. So let's say this curve which I have drawn here, let me call it gamma. Okay, so let's say y is equal to gamma of x, y of x is equal to gamma of x. Okay, so this is the solution which is going to extremize this this functional. And let's imagine a small deviation or variation of this curve. So of course, as I said, the value of the function y should be same at these two endpoints, so it has to be of something of this sort. So I'm imagining a small variation, okay, of away from gamma. Okay, let me write this. So a curve or a function, let me write curve. Okay, you understand that by a curve I mean really a y of x. A curve that differs slightly from gamma can be written as, can be parameterized as gamma plus epsilon eta. Okay, this is a trivial statement. All I am saying is this curve, which is given by some another function y of x, will be to it will be almost gamma, but there will be small deviations which will be controlled by a small parameter epsilon. So epsilon is the small parameter which is going to govern or control how much this curve, dotted curve, deviates away from the curve gamma. Okay, and eta is any function with all the good properties that we may need. Okay, so eta is arbitrary function, so eta of x is arbitrary. Good function. Okay, by good I mean all the properties that one may require are available to us. Okay, and eta is a small parameter. And of course, because this is some different y, okay, but I have already said that the y should not change or is fixed at the endpoint. So this also should, this is just a y, so it should not change its value at the endpoints, which means the epsilon, the eta at the endpoints should be 0. Okay, that's required because I have already assumed gamma to be the correct solution, which means the gamma itself has the correct values that it should take at these two endpoints. So any deviation should not change the values at the endpoint. So that's why you have this condition. Okay, that's good. That's good. Okay. Now, if I take this y, which is gamma plus epsilon eta, okay, and substitute it in this functional, okay, then this functional will not remain a functional, but will become a function, because now I am not anymore changing a function, because eta is going to be chosen to be something, gamma is fixed anyway. The only thing that you are changing is epsilon, okay, and epsilon is a number. So let me define a function phi, which is a function of epsilon, to be this: x0 to x1 dx, and here you have f of x, and instead of y I am going to put gamma plus epsilon eta, and y prime will become gamma prime plus epsilon eta prime. Okay, so that's the definition of the function phi. Okay, note that this is not a functional, it's a function. Okay, because now whatever you change in here is just epsilon. Okay, that's good. Now let's see what happens as we change epsilon. So phi 0 is when you are putting phi 0, epsilon is 0, then you are using the gamma here, right? That's what it becomes. It becomes x, gamma, and gamma prime. And when you are on this curve, then you have this phi of epsilon. Okay. Now let's look at phi epsilon minus phi naught. So we are asking how much the function phi changes as you go from this curve to a neighboring curve, and the difference is clearly x0 to x1 dx. So I'm going to write this for expand it around epsilon equal to 0. So let me write it down as, so the first term in the expansion is f of x gamma prime. Then you have del f over delta y epsilon eta. So here this is the place where y sits. Okay, so I'm looking at the rate of change of f with respect to what you have in here, and then what is the deviation. So it's epsilon gamma plus del f over del y prime. That's the place what you have here is y prime, and the deviation is now epsilon eta prime. Okay, that's the change in the function. So this gives your change in f up to order epsilon, and then of course there will be order epsilon square higher order terms. Okay, that's good. Now I should also subtract phi of 0, so which I can include in here, minus f x gamma prime, and these two of course cancel. Now this term is there, then these two have epsilon in common, which I will pull out and take to the left. Okay, so I will have phi epsilon minus phi 0 over epsilon, and I want to take the limit epsilon going to 0. Okay, and in that limit I have I get phi prime of epsilon, which is phi of epsilon minus phi of 0. Let me put it here, epsilon, and limit epsilon going to 0. Okay, which is phi prime of epsilon. And what is that? It's, so epsilon has already been divided, so you get only these two terms. So let me write that down. You get integral x naught to x1 dx, and in the you have del f over del y eta plus del f over del y prime eta prime. Let's see whether that is correct. That is correct. Very good. Okay. Now remember what we are looking for. We are looking for a way to say that gamma is the one which extremizes this integral, which is equivalent to saying that the function phi of epsilon should have an extremum at epsilon equal to 0, right? Because epsilon equal to 0 corresponds to the curve gamma. So I have changed the problem of finding the extremum of a functional to finding the extremum of a function phi, and that is easy. That I know that if I ask that this quantity be 0, that is phi prime of epsilon is 0, then that is the location where the function could be will have an extremum, or maybe a saddle point. Okay, so at least a stationary point. Okay, so this is the condition that we have, but we can make further progress by using a very useful trick which you will encounter several times in physics and mathematics, that is called integration by parts. So let me tell you about that. I'll use some color so that it appears to be a separate part. Okay, a trick. Integration. Okay, it looks horrible. Integration by parts. Let me say in words what it's going to do for us. You see, what is this? It is df over dy prime, some function. Okay, then you have an eta prime. Eta prime is d eta over dx. Okay, now what I can do by using this trick integration by parts is, let me write down this thing as delta f over delta y prime d eta over dx. Okay, so what I can do is, what integration by parts does is, it helps you to take away the derivative from eta and put it on this one. And that you may want to do because there is an eta here, and then you will be able to combine the two terms. So that's what integration by parts does, and which you have learned in your school. So let me show you again, in case you have not used it before. So all it does is, let's say you have some function f times g. Okay, so there are two functions f and g, and you are looking at a derivative of this product. Then this is, as you remember, df over dg, sorry, df over dx times g plus f times dg over dx. Okay, which means that if I am looking at df over dx times g, so right now the derivative is on f and not on g, and you get f dg over dx plus d over dx of f times g. Is that correct? That is correct. Okay, now if you're looking at an integral of this, left hand side, then it becomes, let me write it dx and put the minus sign here, plus integral of this, right? Let us put some limits, a to b. So you see, here the derivative is sitting on f, but in this one the derivative is sitting on g, and it has been pulled away from f, but you get a minus sign. So you always remember that when you do this, you get a minus sign. And this term is called boundary term because this is equal to what? It's a total derivative, so it will give you f times g evaluated at b minus f times g evaluated at a. And many times you will not have a boundary term because maybe one of the functions is fixed and it's not allowed to change, so this will be 0. Okay, you'll see. But anyway, there is a boundary term, so you should remember these are called boundary terms. Okay, so let's use that in our analysis. So what I can do is I can put the derivative from eta to this one. So there will be a d over dx sitting on this, and eta will be freed up. And as you saw, there is a minus sign, so there will be a minus sign, and then there will be boundary terms. So let's see what we get. So your phi prime of x becomes x naught to x1 dx delta f over delta y, and there is an eta which I will keep outside, and then you get a minus sign, and the derivative is sitting now on delta f over delta y prime. Okay, and there is an eta again, which now I will take common and just make it eta f x to be more explicit. And then this will generate a term of this kind, right? D over dx acting on del f over del y prime and eta. Okay, so you'll get, let me write down, plus so this d over dx will, when you are integrating, it will go away and it will lead you to this. So it is del f over del y prime times eta of x. Okay, and you have to evaluate at the boundary, so it will be evaluated at x1 and subtracted at x0. Okay, so that's what you will get. Okay, let's see whether I missed something or not. Okay, fine, looks good. Okay, very good, nothing has been missed. Now if you look at this one, I have already said that eta should remain, it should vanish at x0 and x1, so that your whatever function this is, it should not change at the endpoints, which means when you calculate these boundary terms, you'll put an eta x1 here, and of course this will be also evaluated at x1, but then this will vanish. Similarly at this boundary also it will vanish, so the boundary term vanishes. Boundary term vanish. Okay, boundary terms vanish, so at the both ends it vanishes. Okay, so now what you are left with is this, which means for an extremum for gamma to be extremum or a stationary point, phi prime of not epsilon, phi prime of epsilon should be 0. So phi prime should be 0 at epsilon equal to 0. Okay, so here this is I'm saying phi prime at 0 should be 0. Okay, I should have been more careful in writing this. Okay, so that's the condition we are looking at. Okay, so what does that mean? It means so for this to be 0, so what I want is this to be 0. Let me write it again. Prime times eta. This is what I want to be 0, right? But if this is 0, then my functional is an extremum at gamma. Okay, that's good. Now it's just a few steps away, or one argument away from the final result. Now because your eta is an arbitrary function, I have never specified what that function is. You could choose it freely. Okay, it should have all the good properties that we want for it, but other than that it is completely arbitrary. Okay, now I can conclude from here that this whatever you have in square brackets is 0. Let me tell you how we can conclude this. What happened? Okay, I need to add a sheet here. Okay, let's go. So let's see how I can make that conclusion. And this conclusion is based on what is called fundamental lemma of calculus of variations. Let me put it again in red so that it appears not to be the main part. So fundamental lemma of calculus of variations. Okay, and what's that? So imagine you are given the following integral, f of x times eta of x, and you are told that this integral is 0 and eta is arbitrary. Okay, so let's say it is told that this is true for arbitrary eta. Okay, and let's say that f of x is not identically 0. Okay, if that is the case, let's say at some point, so I'm saying f of x is not 0. Let's assume this. If I assume this, then it means that the function is going to take some positive or negative value at some point. So let's take a point where it takes a positive value. Okay, so let's say your f of x is greater than 0 at some point. that point, let me call it x naught, and which lies between a and b. Okay, it has some value, non-zero value, and I will assume that the function f of x is given to be continuous. Now if it is continuous, then if it is positive at some point, then it will be positive in a neighborhood of this point, because it cannot immediately become 0, right? So it has to be positive in some neighborhood, and in the same neighborhood, okay, so it's positive in some neighborhood. So let's say f of x would then be positive in a neighborhood of x naught. Okay, right? So that's clear. Now because eta is arbitrary, I can choose eta to be positive in this neighborhood. Okay, in the same neighborhood, I choose eta to be positive. Okay, it may be it may take a maximum value somewhere in the neighborhood, and it may be falling down, and then it goes to 0 outside the neighborhood. Okay, so when it is outside the neighborhood, the function is 0, and in the neighborhood, within the neighborhood, it takes a positive value. Okay, so let me say we take eta x to be positive in this neighborhood, of x naught, and 0 outside. Okay, you can make this choice for eta, but then it is evident that this integral f times eta integrated over this x from a to b will not vanish then, right? Because eta is 0 everywhere outside the neighborhood, so it doesn't care about what f is doing, so that will be 0. Okay, unless these are singular, but we have assumed there are no singularities. Okay, and within the neighborhood where there is a support for this function and eta, support for eta, this is positive, that is positive, so it will give you a answer which will be positive. Okay, which is in contradiction to what we have set out to say, that the integral should be 0, which means that this assumption is not correct. Okay, so we get a contradiction. DICTION, which implies that my f has to be 0 identically. Okay, so if that is the case, then I should first change the color and get black, and conclude immediately that whatever you have in the square brackets here should be 0, right? So this implies that del f over del y minus d over dx del f over del y prime is equal to 0, meaning the function y should satisfy this equation for it to be an extremum, to provide an extremum of the integral. Okay, so that gamma will be obtained from this equation. Okay, that's very nice. We have got the solution to this, and note that if I replaced my f by Lagrangian, x by time, okay, and y by a generalized coordinate q, then this equation becomes del L by del q minus d over dt del L over del q dot is equal to 0, and that's what is your Euler-Lagrange equation, which you have encountered in the very beginning of this course.